move on to tipping points. Speaker will be Martin Claussen from Max Planck Hamburg, and his title is Tipping Points in Biogeophysics. Martin.
Yeah, thank you very much for inviting me to talk about tipping points. I think my talk will be a little different from the others. It's about conceptual thinking and models and data concept. I mean, that's the way I got the paleoplanet, but I think it might be also an interesting approach. So, tipping points, which in this context I would like to loosely define as large-scale abrupt regime shifts frequently occurred in the past, and they are very interesting. First of all, they can come as a surprise. Even if you know the forcing that changes or that triggers these shifts is known precisely, you cannot precisely predict the onset of the shift. And then secondly, if the abrupt shift is abrupt not only in terms of much faster than the change of rate in the forcing, but also faster than the time scale of adaptation of natural and human systems, then it's very important from the socio-economic point of view. So, Tim Lenton and others identified a number of tipping elements in the Earth system. Tipping elements are these elements in the Earth system that reveal tipping points, or potentially large-scale shifts. And there are three biogeophysical points. One is at high latitudes, boreal forest, and the second is the Amazon, and the third here is the Sahara, greening actually. So, in my talk I would like to focus on the later case, because I think there we know best what's going on, and actually we have a lively discussion. I'm not sure whether we really know what's going on, but this discussion is intense at least. So, before I come to the tipping point, the issue, I would like to briefly revisit the three ingredients you need to make the Sahara green. First of all, I consider climate in the wider sense, so consisting of the climate system with atmosphere, ocean, vegetation, and so on, that is forced on the outside. So forcing means not climate forcing the ecosystem, but forcing is something outside that forces the interaction between atmosphere, ocean, and vegetation. And if you think of longer time scales, so thousands of years, then of course the orbital forcing is the main driver, external driver. And basically, of course, the Earth's orbit around the Sun changes, and that would lead, coming from the last glacial maximum to today, to increase in summer insolation in the termination period, and then a decrease from the early to the late Holocene. And that would lead to a stronger warming of the continents in summer versus ocean, simply because of the large heat capacity of the ocean. That picks up the warming a little bit later, so we have a stronger warming in autumn. And that would lead to lower sea level pressure over the continents. That fosters the monsoon. So that's a picture that's known for many years. Interestingly, if you put them into atmosphere modes, I should say, climate modes in the sense of atmosphere only, so the meteorological point of climate, then what you see is that indeed there is some more precipitation, but more in the Saharan zone. It doesn't intrude far enough to the north. So you would not get a really much greener Sahara, or Sahara much greener than today. And actually, if you use one of the modes and use a vegetation mode to diagnose the impact of the increase in the precipitation onto vegetation, you see the sobering point that the Sahara is almost like it is today. So there's no greening. Obviously, the forcing alone is not enough to explain this stuff. And that's quite typical with the climate system. The climate system is highly nonlinear, so the forcing can do something, and then all of a sudden you need something to amplify. And in this case, the amplification is vegetation itself. So here are model simulations by Pascal and myself many years ago, which shows that yes, if you add vegetation, then all of a sudden the increase in precipitation is much stronger. And here in this model you see that the ocean adds to this, and then you get more rain farther north. And if you couple, this is also a couple model, if you take this model, you get a decent greening here in the western part in West Africa up to North Africa. And the colors being here xerophytic woods, so that's not a Garden of Eden, it's a grassland mainly and savanna. Because it's a core-scale model, we don't see what's going on near the rivers and the lakes, so there are no gallery. But on average, you see a decent greening. So vegetation is an important point. I should mention that it's not only vegetation. You have to change also the soils. I mean, if you put in vegetation on the bright sandy soils in the Sahara, well, that's something. But you put also carbon from the shaded leaves on the ground, and the carbon, the soil gets darker. Because the soil albedo, the fertility, is an important issue here in this respect. If you look at today's relative balance at the top of the atmosphere, you see that the Sahara cools the atmosphere, simply because much more radiation is reflected into space than comes in, and there's also warmer, there's a heat radiation goes out. So in comparison with the other region, it's a cooling, Sahara cools the atmosphere, and that's compensated by a change in the airflow, leading to a conversion, the sinking, the alveolar warming, and at the same time, this sinking motion would more suppress the intrusion of the summer monsoon here into this continent, also in the Atlantic. And if you change the color, if you just paint this green, and that's what we do in models, therefore we have color, therefore we have climate, so there's more system models. You do all this stuff to nature that you shouldn't do in reality. So we paint this green, and then this changes completely, and we get a strong intrusion of the monsoon into the Sahara. So that was a mechanism proposed by Shani some 40 years ago. I mean, ironically, Shani proposed this mechanism to explain the Sahelian drought. Now, the albedo changes over the Sahelian over the last decades are not that big, but obviously in the paleo context, that does work. And you see a strong change in albedo over the Sahara. And we have the bright sense here of the Bodele depression, and it was much greener and then much lower reflectant. So it's all this. So now that's the basic stuff. Now, how can we about to think about that this biogeophysical feedback would be strong enough to lead some tipping? So what about the tipping Sahara? How did this term emerge? I mean, we started this business, there were no tipping points in the policy and science, but when playing around with the model, again, I mean, as a model you can do a lot with the model. So for example, you could start the biosphere model by just having desert continents, no? See what's going on, and then you just let the atmosphere vegetation model go, and then the vegetation model is smart enough to bring back vegetation where it should be, and you get a solution that looks like today, and also in Northern Africa you have a big desert. Now if you do the same, but start with forest all over the continents, then the vegetation model again is smart enough to produce all the proper vegetation all over the world, except for Northern Africa. There obviously you get a much greener world than today, and when I found this I said, oh, that's something wrong. Maybe the model is wrong. But then I remembered that I read some weird stuff of crocodiles and some paleo tribes in North Africa. I said, well, let's look at the paleo. So look at mid-Holocene insolation changes, and then do the same exercise, and well, we do get a green Sahara, but too much, to my surprise, we don't get this more sandy solution. So regardless how we initialize the model, from desert world, from forest world, it ends up in this solution. So obviously you get multiple equilibria for present day, and only a single equilibrium for Holocene conditions. Now that's interesting. I mean, it's quite typical for nonlinear systems to have multiple solutions. I mean, think of solving a parabolic equations. We have two solutions. Linear, but of course, it doesn't mean that the climate system is linear in the mid-Holocene. Now, how to reconcile this? And that, well, I need to take you to theoretical physics a bit. I promise you to talk about concepts. Now, think of a vegetation model, very simple, for a semi-arid region, where vegetation depends on precipitation, such that, for example, like this, if precipitation is low enough, you have a desert, and if it's large enough, you have a green world, or the region you consider. And in between, there's some shade. It could be like this, it could be something, but it's not a straight line. It's something like this. Now take the other way around. Take an atmosphere model. and then paint the surface different. So to mimic low vegetation and high vegetation. And what we learned is that with the darker surface you get more precipitation. So that would be a curve like this. So that would be the result of an atmospheric model responding to different fixed vegetation coverages. And if you couple the system, then the solution would be just the intersection point here. Now, imagine that for some reason the precipitation goes down. For example, because of orbital forcing. So something like this. And then you see, all of a sudden, you should have 3 solutions. Well, that's a bit puzzling. I talk about 2 solutions. So a green one, a desert one, and something in between. Actually, that is a dashed solution, so to say, a solution that would not occur in a climate model, nor in reality, because it's unstable to very small perturbations. And how can we visualize this? Well, we can paint a stability function, the ultimate potential in mathematics. And the extreme values of this function are the equilibria. And then you can put the system over here and you can shape it by random fluctuations. For example, weather, or decay precipitation fluctuations. There are a lot in this area. So then you see that in this case, the system is resilient. It stays there. You can click it and it stays there. Now, if you compute the stability function for today, you see, well, this dashed solution is the unstable one. It resides on the maximum at the top of the hill. You give it a slight kick and it jumps either in this direction here or in that direction. Now, the green solution is a stable one, but it's locally stable. If you have stronger perturbation, like it occurs in the Saharan, you can kick the system over the hill into this solution, and you really see this is more resilient, it's more stable. So that would be the explanation that there's no contradiction of finding multiple equilibria, and the real world desert Sahara instead of green. Now that's one point. And the second point is, if you go from Holocene to present day, you see that once upon a time, the stability function should change to develop multiple equilibria. And then you could guess that there would be a time in which there's a likelihood going from green to desert, from one solution to the other one. And that led us to the conclusion that there should be the possibility of an abrupt transition somewhere in between 6,000 to 4,000 BP. Now that was conceptual wishful thinking. Then next we had another model which is fully coupled atmosphere ocean vegetation model, but model of intermediate complexity, what we call it in EMIC, because geography is pretty coarse, as you see. I mean, the Sahara is one grid cell, and the Saharan is one grid cell, so you can just do rough stuff with this. But this model can be calculated for now, maybe of years. Stefan Ramsdorff showed yesterday a movie that's done with this model, so you go over the quaternary. And during that time, to calculate 1,000 years, it's just done within an hour or less. So with this model, you see that indeed, this is a driving, a proxy, so to say, the model proxy for the driving. And this is the vegetation change. You see a fast change. And if you look at this, it's roughly 5,500 years ago. Well, it's much faster than forcing. So to say it's abrupt in some instances, but surely it's not much faster than the time scale of adaptation. So I guess, and then we discussed this with archaeologists, this would lead perhaps not a collapse of a society, like a collapse sense, but more as a transformation. And if you think that during that time civilization moved and built up a new high civilization in the Nile and Mesopotamia, so that might be a trigger. But I don't want to go into detail. I don't think that climate always drives society. That's a more complex issue. Okay, now the line's a bit farther down because a year later, Peter de Mennekel and many others published this paper showing the dust flux into the Atlantic, and the scale is reversed, so there's little dust and there's large dust. Wow, that fits. Now that's a dream for a modeler. You make a prediction of an abrupt change, and then all of a sudden the data people can say, oh yeah, I see this in my data. That's great, and that's the moment when you say, oh, that's an abrupt change, this is a tipping element, and then later on, I think it was Martin Skipper who coined the term then catastrophic shift, and then Sahara is one of the examples, and so on and so on. However, I think even back then, and we put a question mark on simply because this model is talking about the Sahara, and this is a dust flux into this location here. Might be not the same. For example, now it's getting a bit more complicated, so to say. As a scientist, you hopefully have to question yourself. For example, does the dust flux really indicate biogeophysical tipping? Well, it could. But it could just be an indicator of a nonlinear threshold behavior of a hydrological system. For example, imagine a lake like this, and that's due to Sharon Nicholson from Florida, and then rainfall does not change abruptly, but it goes back slowly. You know? And then the lake gets shallower and shallower, and all of a sudden it desiccates. No? So there's a highly nonlinear sort of threshold behavior in response of, I must say, not climate force, not only climate system force. It could be. So therefore, one has to be careful of taking a proxy to interpret something else. It might be, we cannot exclude the possibility that the aspect is not a good indicator of biogeophysical tipping. So what you need really is you need direct proxies, proxies that tell you about vegetation change. And fortunately, we do have such data. Unfortunately, there's only one record so far I know of. That's the record Stefan Köpeling brought back from Lake Yoa. Now that's more on the eastern part. And you see that's rich. You don't see all the details. That's intentional. I mean, so you see there's a lot of things going on. You see here this is abrupt change in the aquatic system, going from a freshwater lake to a more salty conditions, and that's abrupt. But again, it doesn't mean that the rainfall was abrupt. It's just it might be just a threshold behavior, for intrinsic behavior following precipitation change. And you see here a lot of pollen data here, tropical taxa, then Erica type, which might come from the Tibesti, and they fluctuate a lot, and then Poseas is still there. So if you go there to the Lake Yoa, I mean, it's nice. You have a lake right in the desert and with lush vegetation around it. It's a change in biodiversity from the Holocene to today. So there were tropical taxa in the mid-Holocene, and nowadays there are subtropical Saharan taxa. And that concluded Stefan to say, well, that's not a strong feedback. It's just some fluctuations, and actually that goes back to Liu, who said, well, I mean, imagine we have this change in precipitation, I indicated that, and then take a vegetation type like this, that would have the solutions which do not change drastically in time. It's certainly not giving rise to abrupt jump regime shift. So if you take this and then compute the transient behavior of it using some additional weather noise, randomly varying precipitation, without this strong feedback, just by chance, vegetation may be following, reacting to vegetation, precipitation changes. Okay, well, so what is right, what is wrong? Tipping or not tipping? Well, I think we are now starting to get an idea of the complexity of the biogeophysical tipping, because there's much more to it than just having vegetation and it tips or it doesn't tip. For example, first of all, we talk about different regions. I mean, this is a dust core here, and this is Lake Yoa, and I was talking about this region more with the early modeling, and there's another modeling effort by Hans Rensen. It's also affecting Western Sahara, and this is the region thing Leo was talking about with the Lake Yoa. So it's different, and it's sensible to assume that you have different dynamics in different regions. And indeed, Sebastian Battiani, a doctoral student of mine, used a more complex but still rather simple atmosphere vegetation model, which has a lot of spatial heterogeneity. And indeed, what we see that, for example, at that point here, you have this time series, and it has a strong change here at some 6,000 years ago. And that point here, later on, 3.5 years ago, and the multiple equilibria, they look different. At different times, you have different situations. So that means, indeed, having one record from one side, and it doesn't show the rough stuff, doesn't invalidate that another record from the other side should reveal multiple stability, and so on. So the Sahara is not a single tipping element. It's not just everything. So, but it's very diverse, and that's also very interesting. It has this interesting implication. I mean, humans live not on the continent, but they live in locations, in regions, so you could have a surprise in one location, another surprise in another location. So that's it's getting a bit more challenging. Okay, another point that came to me recently is related to biodiversity. Now we're talking about plants, no? So there's one green slime. That's what more or less usually do. But I must say you should have a model that is generally valid. No? So therefore we do it simple. Let's take this one here. For example, let's have a plant type which we for the moment call the tropical taxa. I mean, I'm not good at biodiversity, but let's assume from a theoretical point of view, it looks like this, and this taxa should give rise to an abrupt change in the transition period here. It has three solutions. Now add to this something like this, which I potentially call, just by accident, poor Sea. So something that is more resilient and would not exhibit structure. Now put them together and then respond them to the precipitation, to the same precipitation, the precipitation that sees just vegetation. So something is going on and it doesn't care whether it's tropical or whatsoever. So, and you combine this and what you see all of a sudden, well, you see a synchronous change, and the green stuff here, it looks like a stable collapse. It doesn't look unstable anymore. It's just fluctuating quite a lot. And then here, this is also quite fluctuating. And then finally, things get too dry, and then the tropical taxa can exist anymore. But this is going on still. And that might be a valid interpretation of what we see here in the Lake Yoa. I talk about valid interpretation, might be completely wrong, but we could try to explore this. Okay, so just very briefly, the other potential cases. We do see, one of us, Carlos Nobre and Oyama published this many years ago, see multiple equilibria in South America. The others don't. Now there's a work by Martin Skepper in his group indicating that there might be a potential for multiple stability. So that could be another candidate at high latitude. Well, if we interpret the climate models in terms of this conceptual thinking, we don't see any big change in stability, but the data by McDonald's, yeah, they might indicate something going on here. So still to be explored. So conclusions. I think that biogeophysical tipping is a plausible model for past climate and biosphere change in the Sahara. Now, but it's more complicated than we saw previously. Begin to explore the spatial temporal complexity of biogeophysical tipping. We see that the Sahara is not a single tipping element, and I guess it's the same, it will be true for the Amazon or the border forest. We see that abrupt changes can occur at different times in different regions, and intensity biodiversity plays a trick. I mean, you can conceal a strong biogeophysical feedback, which is, has interesting implication. Imagine that you interfere with biodiversity and purposely, and then all of a sudden you make a seemingly more or less a stable system unstable. Could be, theoretically. The point is actually, from a single paleo record, you cannot uniquely determine the dynamics of the underlying processes. That's a badness. We need more paleo data and also more direct proxies, saying not just the dust flux indicating some vegetation change, which is, but really changes in pollen, changes in indicator of a direct indicator of precipitation. And we need those archives of direct proxy to foster model-based interpretation of data to explore potential surprises in the future, because that has an implication. We have to understand the dynamics to make some assessment for future dynamics. So, thank you very much.
Thank you. Thank you very much for this very nice presentation. My question is about the stability function that you present there. Could you make a map of this stability function across the Sahara, and maybe you can see that?
Yeah, that can be done. I haven't done this, but in principle you can do it. But it changes with time. It's very complex. Yeah.
And also, you say that we need not a single value record. Actually, I present a poster from Lake Yoa, and I show all the proxies.
Okay.
And we see tipping points at different times than the first one that has been presented.
Yeah, the poster, or what do you say? I should visit the poster. Oh, thank you very much. Yeah, I should mention that this is even more complicated in the Sahara because in a spatially heterogeneous case, you might have the case that you have an unstable region and a stable region around, and then you kick the unstable system, and then you reduce tipping to the other one. Could also be very good.
Paul, I think I see.
Thanks. I want to ask you questions about the tipping aspect of the modeling aspect, but I have one concerning the case of the Sahara. As far as I know, the Sahara, it's very difficult to understand its climatic changes without taking into consideration the hydrogeological aspect. I mean, the feeding of the two major reservoirs, the continental Sahara and the continental terminal, which are the two major groundwater systems feeding the water bodies. So how do they come into the scenery?
Yeah, good point. Well, not yet in the model, but the point in the conceptual consideration is there that we think that the groundwater fills up slowly with precipitation, and then you don't see anything while the precipitation increases, and all of a sudden you have the lakes. So, now we haven't had any. We do have hydrological modeling, but not the groundwater aquifer. Also, on the other hand, there is some modeling going on to show the aquifers and potential green corridors that human could have walked in, even in the EMEA. Right? So that,
it's been elusive to get by stability in other climate models. And what, and indeed, sort of Hans Renson's result suggested that it was very important to include the interannual and interdecadal variability, which sort of kind of means that you're always shaking about your simple model there. What are your thoughts about why it's been so elusive to reproducing other climate models?
Well, actually, I do not really know. I mean, we have in our climate model, one does not. We know that the older version has a stronger west-east contrast in northern Africa, getting a better handle on the Saharan heat flow. The newer model is more zonal, and it doesn't have much. So that's, I think, a failure. So we definitely will look into the convection scheme of our models. So if we switch from one convection to the other, it gives a completely different precipitation. And then, yes, with Hans Renson. Now, Hans Renson doesn't see abrupt change, but what in his model is a lot of fluctuation, which we can interpret as a flicker between states. Now, his model, I think he's the old one, the old one has too strong variability. So it might that the strong variability in his model would conceal an abrupt change. Could be.
Okay, Andre.
Yeah. It's precipitation for a tropical region, we might agree. But as soon as you move to the mid-latitude or the high latitude, temperature is going to play a more important role eventually than precipitation. How is the conceptual explanation going with two variables?
Well, yes. First of all, this one here is the same conceptual model, but of course, this is a high latitude forest. We don't take precipitation as a decisive variable, but temperatures. So you can use a different, you have to reformulate the model. Then what I showed earlier, this is the work by Sebastian Battiani. That indeed is, again, a simple vegetation model, but it has both temperature sum and precipitation in it. You can do it, I mean, I tried to make it as simple as possible to understand the principle, but in reality, of course, we have to think out much more. And, yeah.
Okay. You know that in Sahara or sub-Saharan area, the greenhouses are very popular for cultivation.
Yeah.
So, if you cover Sahara by the greenhouses or partly by greenhouses, what result do you expect?
You mean by greenhouses put in by humans there? Or by the greenhouse effect? Because that's also an important point. The greenhouse effect, yes. That's an interesting mechanism. Because what we see in our model, the comprehensive model, is that we have a lot of fertilization of the vegetation. So if we go look into one of our scenario runs, and we see a warming climate, and precipitation does not change strongly, a little bit. But nonetheless, we get a much greener Sahelian, and it moves north. in our model, and that's mainly the water use efficiency, that it increases by increasing CO2. That is an important point that's not yet included here, because we're comparing all the things. But if you have a lot of CO2, that is an important issue. And there are only 3 models so far in the CMF5, the Climate Model Intercomparison Project, launched recently and finalized recently, that have atmosphere ocean vegetation models. It's ours, Hadley Sanders and Japanese NIROC. And the NIROC has the same. Now they have a lot of precipitation, and the Hadley Center doesn't. So if you would like to believe in models, you say, well, I cannot say anything because the models are pretty diverse.
Just, you mentioned in your biostability model, mostly the external factors like precipitation was the main factor. But you didn't mention anything about the trophic dynamics, most of the internal mechanism behind the Sahara landscape.
What do you mean by trophic? The humans?
The trophic dynamics.
Of the plants?
Yes.
Okay, well, yes, if you want to I think that's very good that I put a point up, and thank you very much for this question. I talked about conceptual thinking, and you try to make a conceptual model as simple as possible. Not too simple, but as simple as possible. You really reduce it to the minimum. And that was the first order approximation, if you wish. Now, a comprehensive vegetation model does have, of course, much more complex processes in it, competition between different plants, wet primary reduction, perturbations. I haven't talked about fire, I haven't talked about humans, because humans were there and they're a bit of the same. Well, we can mimic humans by just cutting something somewhere, but it's of course a bit substitute. And we don't know how strong the influence was. And you are completely right, there are much more complications. But here I would like to strip down the problem to a minimum to see what the first order effect would be. Yeah.
Okay. One last question, and we'll have to.
Yeah, I will be out of coffee there, so I.
Yeah, I just wanted to ask you. Suppose you extended your simulation back in time.
Yeah.
Perhaps you look for a few more evidence of paleotipping points.
Yeah.
And will that make sense to do so that you could look for those paleotipping points and validate your model?
Well, actually, there's another point which I didn't show here. Again, it was a very nice surprise to me. I presented a run that goes back to the last 200,000 years, and then say, well, that's the Sahara. It should, if climate is warm enough, the Saharan greening should follow the precessional cycle. And then a young person from Bremen University started, oh, I have the data. And we published this together. It's a paper by Tialinghi and others, and in 2008 or 9 in Nature Geoscience. So yes, if we go back in time, we see this going on and off with the precessional cycle. And during the glacier, the Heinrich events play a role, but that's more to the south. You don't see big changes in the cycle because it's way too cold, too few moisture in the air to make a Saharan greening. But yes, you can go back in time, and you can go back into the future. So just put a lot of CO2 into it, and then go for the next 100,000 years. And what you see actually is that again, I mean, you see the precessional cycle because the climate is warm enough, and it depends on the level of CO2 you pump into the atmosphere. It might be more green or less green, but you have the precessional cycle. So if my prediction is that if we don't have climate change, just the natural climate change, the Sahara will become green again in 10,000 years.
Okay.
Okay, yeah.
Very engaging. We better stop here. Continue over.